Howdy. Alright, so I'm going to run through an example for PDEs. This video is going to be on the wave equation. So I want to take you through the concepts that you need to understand in order to solve this problem. So the question we're looking at is this one in the PDE notes. Number 2. A perfectly elastic string is stretched between 2 points 10 centimeters apart. Its center point is displaced 2 centimeter from its position of rest at right angles to the original direction of the string, and then released with zero velocity. Applying that equation with c squared equal 1, determine the subsequent motion u of x of t. All right, so one important thing to understand about PDEs is that you're going to start off with the most general form of a solution that you've got. Your purpose then is to refine that general solution until you have a function that describes your system well. Okay, so the way you're going to do this is by focusing on the boundary conditions that you have to attain from the data. Yeah, so the boundary conditions are how that system of yours will be refined for a not a general solution, but a specific solution to your specific system. So that's what we want to start with now, is to define all the boundary conditions that we're going to need for this situation. So first, we're going to draw our particular system. So it said you've got a string that is between 1 and 10. So this is your x, and then here is your u of x of t, right? And you're gonna have the string that runs up to the midpoint, right? And at this midpoint, it is 2 centimeters above the reference line, and it sits at the midpoint of this, so that's 5, right? So a couple of things that you need now are, again, the boundary conditions that you're going to use to refine your equation. So the first obvious ones are the position, the displacement of the string at the endpoints. So at 0 and at 10, regardless of the time, right? Regardless of the time that passes as the string oscillates back and forth, these 2 points will always be, the displacement of these 2 points will always be 0. So that's going to be your very first condition. So u of x, or rather, no, not x, u of 0 of t. So at this point, for any time t, the displacement will be 0. Then u of the other endpoint, which is 10 of t, for any value of time at that specific point, the displacement will always be 0. Then the next condition you've got is, they tell us here that um, the string is released with zero velocity. So that's your next boundary condition, is that at and at time 0, the velocity of the system, right, at t equals 0 is 0. Then we need to take a look at the the displacement of a specific point P on the string, right? So as you go along this x-axis, what how can we find what specific point, what the displacement of a specific point is? And you should remember that these lines here are linear, so you can just use the linear equation to find this that describes this linear line, and you'll also do it for this one as well. And it's going to apply for this specific line. It'll be between the range of 0 and 5, and for this line it's going to be between 5 and 10. So then we need to now find what this linear equation is going to be. And the general form for such an equation, uh, we call it f of x, right? F of x is technically the equation for the whole string, but because you've got this change here, you can't describe it with one equation. You have to describe it with two and specify that um, uh, each each part of the line is between these specific ranges, and you'll see how that plays into effect uh, when we have to use these later to find one of our constants. So f of x is equal to y, which is equal to mx plus c, right? So the first thing we want to find is m, which is our gradient. The gradient here will be the change in y, rather let me just get straight to it, y2 minus y1, and y in this case is going to be our displacement here, and x2 minus x1. So y2 is equal to 2 minus y1, which is equal to 0. Alright, that is going to be over x2, which is 5, minus x1, which is 0. That then equals 2 over 5. So that is our gradient. Then we can evaluate uh, to find, because we've got our gradient now, but we need to find c. So to find c, we can evaluate a point that we can observe on here in order to find c by plotting those points in our equation and then solving for c. So we're going to choose this point here at the peak. You can choose any point actually, but because we have these definite values here, we can enter it into our equation. So at this point here that we call P, whatever, we're going to have y being 2, which equals to 2 over 5 multiplied by x at this point is 5 plus c. So if you then solve for c, this will cancel out. Then if you take that over, that will also cancel out. C is going to be 0. So f of x is then equal to 2 over 5 x within the range of 0 and 5. So that describes this linear line here. So now we need to describe this one as well. So we'll do the exact same process. See if I can fit it right next to it. So I'm not going to write this again. Let's just go straight to finding the gradient, and we'll use the exact same formula. And in this case now, our y2 is going to be 0, and that gets subtracted by y1, which is 2, and then x x x2 is 0, which gets subtracted by x1, which is 5. So that oh, my apologies. X1 is equal to 10. So you're going to have minus 2 over 5. There you go. So that's your gradient now. Then you can again input whichever value, um, whichever point on this line that you want to find C. And in this instance, I'll just use this one here. So at this point here, y is equal to 0. So minus 2 over 5 multiply, and x is equal to 10 plus c. So this will give you 2, which then multiplies with that to give you negative 4. So if you take that over, c is then equal to 4. Alright, then f of x is equal to minus 2 over 5x plus 4 between the range of, not 0 this time, no, it's between 5 and 10. Cool. So this should give us all of our boundary conditions, pardon me, that we need in order to evaluate this particular problem. Okay, now we need to talk about the general solution that we are going to use to these boundary conditions to refine. You are expected to assume a general solution for u being some function in terms of x multiplied by some function in terms of t. Alright, and so we also have our initial differential equation here, which is this, so we can just write that down. So d squared of u over dt squared is equal to, so c squared is equal to 1. So I'm not even going to bother writing it here, because this will just become 1. So you can just write this d squared of u over dt. Over dt. Cool. So for this super general solution, we want to now get it to match the order, the differentiated order of this here. So we're going to find d of u in terms of x. So this is the partial differential of u with regard to x. That's going to be x prime times t, when t is a constant. then d squared of u is equal to dx squared. Now, keep in mind, the first part of this is literally just memorization work, um, with the exception of this function here, because that depends on the actual values of your table. But everything else is just pure memorization, and there's nothing much to it. So then the double partial derivative now is x double prime of t. I mean x double prime times t. So then we can do the same for t now. du of dt is equal to x t prime d squared of u is equal to d dt squared is equal to x double prime. All right, now we can represent this equation with these symbols here. That just simplifies it for us. So then we write here d squared of u. This is actually supposed to be x. Made a mistake here. All right, cool. So d squared of u over dx squared is this over here. So we just fill that in its place. D double prime multiplied by t, and then this partial differential is going to be x t double prime. Then we can use separation just to get all of the like terms together. That's going to give us x double prime over x, which equals to t double prime over t. Okay, now this is another thing that you have to memorize, is that these ratios give you an equivalent constant value. That constant value we just represent as minus p squared. Okay, it just helps with solving these particular differential equations. So we can then write each one of them equal to this and solve for it. So you've got x double prime over x is equal to minus p squared, and then t double prime over t is equal to minus p squared. Okay, so now we just um, simplify this, or rather multiply each side by the original variable. So minus p squared x, this side is going to be t double prime equal to minus p squared t. And you take both of those over, x double prime minus p squared plus p squared x is equal to 0. And here you've got this is equal to plus p squared t is equal to 0. Okay, so both of these now are in a standard solution, a standard form, which has a standard solution. So the solution of x is equal to a cosine p x plus b sine px. Okay, and the solution for t is the same. We'll call this constant c now, c cosine. Just don't get confused with these. I've had many instances where that can get confusing, and when you like use parentheses, like it looks like a C, so it just looks very weird. But yeah, carrying on. P of t. This one's in terms of t. This one's in terms of x. Plus d sine p of t. Cool. Okay, so that means that our general solution, u of x of t, can now be written as this: u of x and t is equal to, these are brackets, a cosine px plus b sine. Ah, this video is going to take so long. Px multiplied by c cosine pt plus d sine pt. Alright, so this is now a little bit more of a refined solution, but it's still too general for a use case that we have, and that is describing the motion of this particular string here. So what we're going to do to refine this, as we said again, is use the boundary conditions to refine our general solution. So the very first one we're going to use, the very first pair, are these two here. The displacement of the string at the critical points. So the first one, u of 0 t. Um, let me actually not write. Let me not write that. Let me just write what the value of that is. Actually, hold on. Let me do this. So equals to 0, right? Therefore, 0 is equal to uh, a cosine p x. Oh no, not x. X now is 0. P0. And in fact, all of this will just tend to 0. It will just be 0 because you're multiplying by 0. So let's not even bother writing p. 0. Alright. Plus b sine 0. And that is all multiplied by this here. So this will stay as is. And instead of wasting my time, let me rather do this. Yeah. So only x takes on a specific value of 0. T remains t, because that, as we said with that boundary condition, no matter what time passes, that specific point, the displacement at those critical points will always be zero, right? So now we can evaluate what this will be. So A cosine 0 is equal to 1, right? So A is going to stay as is, but sine of 0 is equal to 0. So all of that will just fall away. And so this is all you'll have left. Yeah. So keep in mind, all of these, all of these angles are in radians. That's something that's super important. You will fail if you don't consider that. Anyway, so now we've got this expression here, right? And we need to ask ourselves what value here, what one value here is going to make all of this equal to 0. And the only culprit we've got is A, right? Because if you make either of these 0, then you're still going to have um, a term that is not 0. So it means A is equal to 0, right? So now we've refined our solution a bit more by finding the value of this constant um, by using this initial condition. So then we can take this value and place it the into the general solution that we had earlier, right? So then it's going to become u of x of t is equal to, with a being 0, only thing you'll have left is b sine p of x multiplied by, yeah, let me not be that guy here. Technology. Watch this. Boom. Boom. Cool. Okay. So now this is a more refined solution that we've got. So we're gonna keep doing that now until we run out of boundary conditions and we have this thing refined to the best that we can have it. So the next one, I said we were using the first pair. So the next one now is evaluating when x is 10. All right. So at this point, it's going to be equal to 0, right? Now we're now we're substituting this into our refined solution. So we've got 0, right, is equal to b sine um, before I do that, I need to do this. Okay, so p, this is something else that you need to memorize. P times c is equal to lambda, right? P being this variable here, c being the the this constant here, and because c is equal to 1, p will just be equal to lambda. This this it this they use this specific um, symbolism because lambda Lambda kind of means something in terms of Fourier because that's what we use to evaluate this. It's nothing that's too big of a deal, but just do it. Okay. So we're gonna have lambda and evaluating when x is 10, right? Lambda 10 multiplied by c cosine. I keep trying to do this when I've got this option here. Silly goose. Okay, cool. And again, t remains t because we're evaluating this for any value of t. Now, again, what is the value of one of these factors, these terms, that is going to give us 0? We can't we can't have it be b, unlike we had it being a before, because if b is 0, then this whole solution is 0 for all values of t, for all values of x, which basically renders the solution useless to us. So we'll go. That only means then. That means then that sine sine of lambda h, lambda 10, lambda 10 has to be equal to 0. Okay, and lambda 10, right, which is our variable, inverted commas, in this case, is can simply be seen as the value expression for our increment of pi, right? It can just be seen as another way of writing this. Like, um, if you have, say, 4, right? That's also equal to 2 times 2. It's the same thing. So technically, these are the same things. It's this here, right, is what is used um, when we're considering it in radians, and n is just the I'm just trying to find the right word. It's the iteration of that process. So n, can be any number from 0 to positive infinity. Cool. So now we're going to solve for lambda, because that's what we are interested in this case. Uh, Something I didn't change here. We're interested in lambda because it's now this one variable that we 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 don't have, this constant that we don't have, or yeah, actually a variable. Let's call it that because it changes. Okay, so we can solve for that. N pi. Wow, just hit the 30-minute mark. It's crazy. N pi over 10. I'm barely halfway. Anyway, so now we can again input this solution into our into our refined solution to get an even more refined solution. So mu of x of t is equal to, now this b here can be distributed into this bracket, and so the constant p can then be expressed as the product of b and c, just to simplify everything, and the constant q can be seen as B times D, right? So B times C is going to give us P. B times D gives us Q. All right. So then we've got sine of now no longer lambda, but n pi over 10 multiplied by x right here. And then inside our brackets, we've got P, this constant here, cosine let me copy this. That value of lambda, and our variable in this case is t, right? Plus q sine uh, that multiplied by t. Okay, now we have an even further refined equation thanks to our wonderful boundary conditions. So what do we do next? Just keep going with our boundary conditions until we have no more left. But the first thing we want to do is, since now we've got this equation which is expressed with n, and n is an integer value between 0 and let's say r, right? Whatever value, then we can rewrite this as now that a more general term, r being whatever value of n that it may be, that you are evaluating it up to, and u of x of t would then be the sum of all these values of n up to r. So u of 1, u of 2 when n is 2, u of 3 when n is 3, up until u of r, right? So we can then represent that symbolically by using a summing. What is that symbol called? It's the summing operand, something like that. Okay, you geeks can find that out for me. Okay, so we've got then the summation of n equals to or um, actually we started at 1, not 0, because yeah, we started at 1, right? And then we take it to and then we take it to infinity. Let me just make sure. Hold on. Okay, yeah. So it is actually from 1 to infinity. So this is evaluating the eigenvalues and eigenfunctions for every possible value of n. So let's get back to back to the mission. Okay, so that is the summation of sine r of pi what I find weird about this is that we make n equal to r for a specific value that we're evaluating this up until, but we sum it to infinity. So I mean, if we're going to do that in the first place, why not just keep n? Because that's what we represent as like the every single possible value that every single possible integer value that can be had in our solution. But okay, the mathematicians, the mathematical gods decided that it is such. So hey, let's not question them, right? We can question them, we can question them, but for the sake of passing our exams, let's not question them. So PR, we are this becomes, yeah, it becomes PR. Suppose because that can change. Then cosine r pi over 10 t plus qr sine of r pi over 10 t. Alrighty. Man, I realize this is actually quite a lot to grasp. Perhaps. I don't know. It seems easy to me because I understand it now. But I mean, we've been going for 40 minutes and we're still not done. But yeah, anyway, hey, you gotta do it. You gotta understand it somehow. Anyway, we now have an even more refined general solution. Alright, so the next thing we're going to do is, again, refine this by finding our constants PR and QR. To find PR, we're going to use Fourier, right? Because this this should remind you of a Fourier series, and this is where Fourier series actually falls into partial differential equations. It's in evaluating the the uh, the the boundary conditions, or the different values that these variables can take, right? So PR is equal to 2 over t, so over 0 to t. This is now this is where we use those equations that we found earlier, right? F of x multiplied by sine n pi of x over t. Let's just make sure I got that right. Yeah, cool. So then we can substitute. So it's 2 over the period, which is 10, because that's the entire length of our string. It's 10. And remember, f of x takes on two functions at two different intervals. So the first interval is 0 to 5, and f of x at this point is 2 over 5x. So that's multiplied by sine n just becomes r pi of x over our period once more, plus Now the second function that f of x becomes, so between 5 and 10, it is minus minus it's minus 2 over 5x plus 4, yeah, and that's going to be multiplied by sine r pi of x over 10. All right, so this is where the actual hard part of this problem comes in. Everything we've done so far is actually like super straightforward. Alhamdulillah, it's straightforward to you. It's actually super straightforward. Inshallah, it's straightforward to you. I don't know why I said Alhamdulillah, but okay. Um, so, to make it easier for ourselves, we're just going to evaluate each of these on its own and then add everything together. But first, before we do that, usually they take this constant here and they just shove it with p, so it becomes like 5. It will become 5pr. So we can represent these two as just I1, the integration of part 1 plus the integration of part 2. Okay, so let us go ahead and solve that. So for I1 now, right, it is 0 to 5, 2 over 5 x sine r pi of x over 10. Okay, and it's in terms of d of x. So we're going to use integration by parts to solve this, because we've got two functions multiplied together. So u of dv is equal to uv minus integration of v du. What we're going to choose as u here is 2 over 5x, means du is equal to this derivative, which is just 2 over 5, right? dv then is equal to sine r pi of x over 10, and so its integration is going to be negative cosine. Wait, it's not just negative cosine. You're doing, they call what, chain rule. Yeah, so the constant in here gets inverted and then multiplied with the original function r pi sine. Yeah, I always make this mistake. Don't make this mistake. Don't be like me. Don't be like me. When you integrate, change your trigonometric ratio. Don't write sine again, bro. Well, you're gonna have big problems. Big problems. Anyway, I'm even at the end of my page here to extend it. Alright. Yeah, 50 minutes. That's crazy. Okay. Yeah, so now it's going to be u, which is 2 over 5 x multiplied by v, which is 10 over r pi cosine r pi of x over 10 minus, well, actually, it's just going to become plus because of this here. 10, I'm going to just straight up factorize this, or just take it outside of this. So yeah, 0 to 5. Technically this is also like evaluate from 0 to 5. Just give me 1 minute. Yeah, anyway. Here we've got cosine r pi of x over 10. That is multiplied by du, which is, oh snap, this is in terms of dx. You should always have your d of whatever variable you're differentiating in terms of. We are diligent students. Anyway, 2 over 5 d of x. And you know what? I'm just going to go ahead and multiply that in here, right? So this becomes 4 over r pi, because that will divide that to 2 and then multiply that by 2 will give you 4. Okay, 4 over r pi. We can just get this rid of this here. Lacquer, man, lacquer. Now this is going to become again 4 over, but negative 4 over r pi, right? Cosine r pi x over 10, correct? I'm not going to include this here because we can just evaluate the entire formula over this range once we've integrated this part here. Makes no difference at all, and it saves me more writing. Okay, so 4 over r pi now, and when we integrate this, it's going to become 10 over r pi sine r pi x over 10, right? And that is all evaluated between 0 and 5. So we can just simplify this. I'll just do it right here. So it becomes forty over r squared pi squared. Okay. So that is now we have to evaluate this over those two limits. Just make sure I'm not writing nonsense. Yeah, I mean, looks alright so far. Cool. Okay. Yeah, this has an x variable. I don't know why. I almost forgot that now. not forgetting any other variables, right? Nope. No. Cool. So it's minus 4 times minus 4 times 5 over r pi cosine r pi 5 over 10 plus 40 over r squared pi squared sine r pi 0 over getting ahead of myself, 5 over 10. That is all subtracted by 4 times 0 over pi cosine r pi r pi 0 over 10 plus sine r squared pi squared sine r pi to 0 over 10. Okay, so this whole bracket here is just going to be 0 because 4 times 0 is 0. That's going to cancel all of this out. R sine of 0 is 0. That also cancels that out. So all you got left here is this minus 20 over r pi cosine r pi over 2 plus 40 over r squared pi squared sine r pi over 2. Yay! We have now solved the first integral. Now we have to do the second one. Yay! I think I should just skip that. I think I should actually just skip that. You should know how to. I mean, if you literally just follow this exact same process, except f of x will now become this function here, and you'll just evaluate that over 0 and 5. So I'm just going to write what that answer is. I2 is equal to, I've got it here somewhere. Yeah, so I2 is equal to 20 over r pi cosine r pi over 2 plus 40 over r squared pi squared sine, it's a horrible sign, sine r pi over 2. Okay. Now we're going to substitute all of that into here. So it's 5pr is equal to minus 20 over r pi cosine r pi over 2 plus 20 over r pi cosine r pi over 2, then plus 40 over r squared pi squared sine r pi over 2 plus another 40 r squared pi squared sine r pi over 2. Okay, yeah, and that'll just simplify to 80 over r squared pi squared sine r pi over 2, divide 80 by 5 and you get 16. So PR is equal to 16 over r squared pi squared. Yeah, sorry for my handwriting, I'm just trying to rush now. Although I think my handwriting has always been trash. Anyway, r pi over 2. Cool. Trash, but I still get these A's, boy. Still get these A's, boy. Anyway, now we can substitute our constant, well, it's no longer a constant, into the most refined solution that we've got, which is this one here. Okay, so u of x of t is now equal to, it's now equal to, and actually, you know what I'm going to do? I can't actually. Okay, so sine r pi over 10x multiplied by 16 over r squared pi squared sine r pi over 2 cosine r pi over 10t plus q of r. Oh yeah, and then this has to be summed over infinity. R is equal, oh gosh, r is equal to 1 to infinity. Sine r pi over 10t. Just make sure that's fine. Yeah, cool. So this is now the most refined that our solution is. We have one more boundary condition that we need to take a look at, and that's going to help us find q of r, and that is d of u of t. The velocity of the string is 0 at time equal to 0. Okay, so we now need to differentiate this whole expression here in terms of in terms of t. So d of u of x of t over dt is equal to 0 at t is equal to 0. Sheesh. At t is equal to 0. My handwriting is starting to look like Muhammad's. Okay, cool. So I'm just going to write 0 because that's what the differentiation equals to at t equals to 0. So then the summation r equal 1. So this is treated as a constant. It'll stay exactly as is. Sine r pi x over 10. This is also a constant, but this is not a constant because it's in terms of t now. So we're going to have that 16 over r. Yuck. 16 over r squared pi squared, right? That's multiplied by sine r pi over 2. Then that's differentiated, so it's going to become minus 10. No, when you differentiate, it stays exactly as is. R pi over 10 sine r pi of t over 10. Yeah, okay, and that's now added with q of r. So this will become, oh yeah, before I forget, time is equal to 0. So this whole thing here is multiplied by 0. So q of r, right, is then multiplied by this differential. So r pi over 10 ah, r pi over 10 cosine r pi. Okay. I wanted to fit that 0 in there, but I mean, this all evaluates to 0 anyway, so I'll just write this 0 here, right? 0 over 10, because we input 0 here, so in effect we'll make that whole top the numerator 0, and yeah, the denominator as well. All right, so we know that sine of 0, because this whole thing is 0 now. Sine of 0 is 0. So this entire term here will cancel out, right? This entire term here will cancel out. Cosine of 0 is equal to 1. This stays as is. So 0 is equal to the, again, is equal to the infinite summation from r equal to 1 of sine r pi of x over 10, right? Q of r pi over 10, the cosine becomes 1, so we're not going to write it there. So then the only value here that can be 0 is q of r. This is a constant, it's not a variable. This here also is a constant, or at least in this specific case we treat it as such, because r will technically have a value. Yeah, so then, and actually it won't make sense to make r 0, because again, if it's 0, then this will always be 0, right? Therefore q of r is equal to 0. That's the only viable option we have to make this expression equivalent. Yeah, so with all of that refining, we finally will have the most um, the most filtered out expression that we can possibly get, with all of the boundary conditions that we've gotten, that will be useful to us in this specific use case. That is describing uh, the the position at a specific point in time of a length of string. Okay, so now that we've got this QR, we're going to submit it, substitute it into our most recent into our most recent iteration, the most recent refined form, which is this here. So u of x of t is equal to summation of sine r pi of x over 10, right? That's multiplied by 16 over r pi r squared pi squared sine r pi over 2 cosine r pi over 10 t, and this here is your general solution. So if we take a look at the answer for this question here, question 2, right? Here's the answer, and it's exactly the same as this one here. The only difference is that they factorized 16 over pi squared. They just took it out here, and they left 1 over r squared. I suppose that's because they wanted to have all of the constants outside, but that doesn't change anything. If you want to write it like this, you can. Otherwise, this is perfect. All right, so that is an example for the wave equation. It took a really long time, and I suppose it's because of the conceptualization that we had to go through. Just trying to get you guys to understand what's going on exactly, so that you're not just memorizing things, but you build an intuition solving these problems. Um, like I said, some of it is just pure memorization work. In fact, you can even say most of it. Like this part here, this deriving the partial differentials for the general solution. That's all memorization work. It's not like we specifically try and find this. Nah, you just must memorize that. Um, where you have to actually think about it is when you're doing the boundary conditions, right? And that's based on your data from 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 the question itself. But most of the time, it's going to follow a very specific format, and you're going to get most of these as they are, with just different values sometimes, except for your extreme points. Those will always be zero, at least for simple questions. I don't know how that would change with more complex ones. But yeah, um, this is good. This is good enough. With this, you will definitely be able to attempt um, standard equations. I'm going to do the heat equation next. It's already 9 o'clock. Am I going to do it tonight? I don't know. Let's see how I feel. Maybe not. But with the heat equation, it's going to be exactly the same process. It's just a bit different. It's a bit different because of the boundary conditions that you work with and the actual equation. The actual equation here, you've got the second differential in terms of x times 1 over c, but only the first differential in terms of t, not the not unlike the string equation, which is both of them are differentiated twice in the equations. There's that, right? That's one distinguishing factor. Then there's how the boundary conditions work, right? It's a bit different as well. That's something you have to pay attention to, and in effect, the the general solutions will also look a bit different, right? But from that point onwards, it's literally going to be exactly the same the um, as the wave equation. Just evaluating after you plug in a few of your boundary conditions, evaluating for like r in terms, um, making that a summation to infinity, and using Fourier to find some what's this some variable, right? Bada bing, bada boom. That's essentially all you're going to be doing. But yeah, that's it from me.